There is a planet in this solar system that could swallow every other planet whole and still have room left over. Its magnetic field stretches wider than the diameter of the sun itself. Its radiation belts would kill an unshielded human in a matter of hours. Winds inside its atmosphere tear across the cloud tops at more than 300 miles per hour. And beneath those clouds, pressure rises so violently that hydrogen stops being a gas, stops being a liquid, and becomes a metal that has never existed naturally anywhere on the surface of Earth. You have seen this planet your entire life. You learned its name in school. You have probably never once thought of it as violent. That is about to change. If you enjoy deep science that goes beyond the surface, consider hitting like and subscribing. It helps more than you know, and it keeps episodes like this one coming. Are you comfortable? Now, let's begin. You already know Jupiter. That is the problem. You have known it since you were a child. It was the big one, the striped one, the planet with the red dot on every poster taped to every classroom wall you ever sat beside. You know it is the largest planet in the solar system. You know it is a gas giant. You know it has moons. You have probably seen photographs from spacecraft and thought to yourself that it looks beautiful, that the swirling bands of cloud are almost like art, that the great red spot is dramatic in the way a painting of a hurricane might be dramatic. Impressive, but safely distant. A spectacle on a wall. And every single part of that comfortable familiarity is a lie. Not a lie in the factual sense. Jupiter is the largest planet. It does have stripes. The red dot is real. But the feeling that comes with recognition, the sense that knowing a planet's name means understanding what it actually is, that is where the deception lives. Because Jupiter is not what the posters show. Jupiter is not a gentle giant floating photogenically through the outer solar system. Jupiter is a world of such physical extremity that nearly every measurement scientists take from it comes back reading as a kind of violence, and the deeper they look, the worse it gets. To understand why, you need to start at the beginning. Not the beginning of the solar system, but the beginning of what you think you see when you look at Jupiter through a telescope. Because the very first thing Jupiter takes from you is ground. There is no surface. You need to hear that clearly because human intuition resists it. Every planet you have ever walked on or imagined walking on has a surface. Mercury has one, Mars has one. Venus, beneath its acid clouds, has one. Even the moon has one. Your brain is wired to assume that a planet is a place with a floor. Jupiter has no floor. What you see when you look at Jupiter's cloud tops is the outermost layer of an atmosphere so deep that it does not end at a boundary between gas and solid rock, the way Earth's atmosphere ends at the ground. Instead, Jupiter's atmosphere just keeps going. It thickens, it compresses, the gas becomes denser and denser under its own weight until, thousands of kilometers down, it behaves more like a fluid than a gas. And then deeper still, it transforms into something that has no equivalent anywhere on the surface of any world you have ever known. There is no moment where you hit the bottom. There is only a gradual, violent compression that would destroy anything human beings have ever built long before it reached the deepest layers. Jupiter does not have a landscape. It has a gradient, a slope of pressure and temperature that steepens until the numbers become difficult to believe. But before you get anywhere near those depths, you have to deal with what is happening at the top. And the top is already more extreme than most people realize. Jupiter's visible atmosphere, the layer you can actually see in photographs, is a churning system of ammonia ice clouds, ammonium hydrosulfide, and water vapor, organized into alternating bands of east-west wind called zones and belts. These bands are not decorative, they are jet streams of staggering power. Winds along some of these bands reach speeds above 600 kilometers per hour. On Earth, the most powerful hurricanes ever recorded produced sustained winds of roughly 300 kilometers per hour, and those storms devastated entire regions. Jupiter sustains winds twice that speed as a permanent feature of its atmosphere, not as a temporary event, not as a seasonal anomaly, as a baseline condition. The wind never stops. Now picture the scale those winds operate across. Jupiter is enormous in a way that the word large does not communicate. More than 1,300 Earths could fit inside it. Its diameter is roughly 140,000 kilometers. If you could somehow place Earth beside Jupiter, the planet you live on would look like a marble sitting next to a basketball. And the basketball would be spinning so fast that a single day on Jupiter lasts only about 10 hours. That is the fastest rotation of any planet in the solar system. A world so massive that it could swallow every other planet, and so restless that it completes a full turn before most people finish a workday. That rotational speed is part of what drives the atmospheric violence. The Coriolis effect on Jupiter, the force created by a spinning body that curves the path of moving air and fluid, is ferocious. It stretches storms into bands, it pins cyclones to the poles, and it sustains wind systems that have been running continuously for longer than human civilization has existed. And there is something else the familiarity hides. Jupiter has rings. Most people do not know this. Rings are Saturn's signature, the feature that defines the planet in the public imagination. But Jupiter has its own ring system, discovered by Voyager 1 in 1979, and its nature reveals something important about the kind of world Jupiter is. Unlike Saturn's bright, icy, visually spectacular rings, Jupiter's rings are faint, dark, and composed primarily of fine dust particles. They are nearly invisible in reflected sunlight and were undetectable from Earth until a spacecraft flew close enough to see them from the right angle. The reason they are so different from Saturn's rings is that they are not ancient stable structures. They are a continuously replenished debris field. Micrometeorite impacts constantly strike Jupiter's small inner moons, Metis, Adrastea, Amalthea, and Thebe, blasting dust off their surfaces. That dust drifts into orbital paths around Jupiter and forms the rings. But the dust does not last. Jupiter's intense radiation environment and the planet's powerful electromagnetic forces degrade and remove ring particles over time. The rings persist only because fresh dust is generated faster than the old dust is destroyed. They are not a permanent feature preserved from the planet's formation. They are a cycle of impact, ejection, orbital drift, radiation destruction, and replacement, running continuously, maintained by the same forces of violence that define Jupiter at every other scale. Even the rings, the feature most people do not know exists, are an expression of the planet's hostility. The Great Red Spot is the most famous of Jupiter's atmospheric systems, and even it has been misunderstood. Most people picture the Great Red Spot as a storm, which it is, but they picture it the way they picture a storm on Earth. Something temporary, something that blows through, something that begins and ends. The Great Red Spot is not temporary. It has been observed since at least the 1800s, and it may have existed for significantly longer than that. It is an anticyclonic storm, meaning it rotates opposite to the direction of cyclones. Its wind speeds exceed 400 kilometers per hour at the edges, and when it was first measured with modern instruments, it was large enough to fit 3 Earths side by side across its widest dimension. That last detail contains its own kind of horror. A storm large enough to hold 3 Earths. Sustained for centuries. Winds faster than anything ever recorded on the planet you live on. And yet, to Jupiter, the Great Red Spot is not exceptional. It is one feature among dozens. It happens to be the largest and the most long-lived. But Jupiter's atmosphere produces enormous oval storms across both hemispheres constantly. Some of them last decades, some of them merge with each other and grow. The Great Red Spot itself appears to sustain its energy partly by consuming smaller storms that drift into its path. Recent research published in 2025 suggests that the spot has been shrinking for over a century precisely because the supply of smaller feeder storms is diminishing. The storm is, in a sense, starving. Once wide enough to span 3 Earths, it now barely spans 1. It is growing taller as it contracts, its structure compressing vertically as it loses horizontal scale. Scientists at NASA's Goddard Space Flight Center have noted that the next 5 to 10 years could bring rapid changes in its behavior. The storm may stabilize at a smaller size, or it may break apart entirely. And a separate historical study published in 2024 revealed something even more disorienting. The Great Red Spot you see in modern images may not be the same feature observed centuries earlier. A dark oval that astronomers in the 1600s called the permanent spot occupied a similar latitude on Jupiter, but appears to have vanished from the observational record for over a century before the modern Great Red Spot emerged in the 1800s. The researchers concluded that these are likely 2 different storms entirely. The earlier one died. The current one was born separately and may someday die as well. Jupiter's atmosphere does not preserve its storms out of loyalty. It creates them, sustains them for as long as conditions allow, and then lets them starve or shear apart without ceremony. The Great Red Spot is not eternal. It is simply the current occupant of a planet that generates storms large enough to swallow worlds and discards them when they're no longer fed. And even if it vanishes, Jupiter will still have its polar cyclones. This is one of the discoveries that the Juno spacecraft delivered after arriving at Jupiter in 2016. Before Juno, nobody knew what Jupiter's poles looked like in detail. The planet's axial tilt is so slight and its distance from Earth so great that telescopes could never get a clean view. Juno changed that. When the spacecraft's instruments looked down at Jupiter's North Pole for the first time, they found something no model had predicted. 8 massive cyclones arranged in an almost perfect octagonal pattern surrounding a single central cyclone. At the South Pole, a similar arrangement existed with 5 cyclones encircling a central one in a pentagonal formation. Each of these storms is roughly the width of the continental United States. They are stable. They persist orbit after orbit, year after year. Their geometric arrangement suggests deep structural forces organizing the atmosphere at levels far beneath the cloud tops. Juno's microwave radiometer confirmed this. The instrument was designed to peer through Jupiter's upper clouds and measure thermal radiation from deeper layers. What it revealed was that Jupiter's atmospheric weather layer does not end a few hundred kilometers down, as some models had assumed. The jet streams and storm systems extend thousands of kilometers into the interior, far deeper than anyone expected. The atmosphere and the interior are not separate systems. They are continuous. The storms you see on the surface are the visible tips of structures that plunge deep into the planet's body, like roots extending downward into an increasingly extreme environment. Juno also discovered phenomena that had never been anticipated. Lightning on Jupiter had been detected before, but previous missions had found it concentrated deep in the atmosphere, in the water cloud layer far below the visible surface. Juno found something different. Its instruments detected shallow lightning, electrical discharges occurring high in the atmosphere in regions dominated by ammonia ice rather than water. On Earth, lightning is generated by the interaction of water droplets and ice crystals inside storm clouds. On Jupiter, a completely different mechanism appears to be at work. Scientists propose that a process involving ammonia acts as an antifreeze, mixing with water ice at high altitudes and creating a slush of ammonia water hailstones that Juno researchers informally named mushballs. These mushballs carry charge as they fall and rise through the clouds, generating electrical discharges in a region of the atmosphere where lightning should not have been possible, according to any previous model. Jupiter was not just producing familiar weather at larger scale. It was producing weather that operated through chemistry and physics that do not exist on Earth. The mushball hypothesis also helped explain another of Juno's puzzles. The microwave radiometer had revealed that ammonia in Jupiter's atmosphere was distributed unevenly, depleted in some bands, and concentrated in others at depths far below, where it should have settled uniformly. The mushball mechanism offered an explanation. If ammonia water hailstones form at high altitudes and fall deep into the atmosphere before evaporating, they would effectively transport ammonia downward in localized plumes, depleting it from the upper layers in some regions and enriching deeper layers in others. Jupiter's atmosphere was not simply turbulent. It was running its own internal redistribution cycle, moving material vertically across thousands of kilometers through a process no one had imagined before Juno arrived. And then there was water. One of the most important questions Juno was sent to answer sounds deceptively simple. How much water does Jupiter contain? The answer matters far beyond chemistry. The amount and distribution of water inside Jupiter directly constrains where in the solar system the planet formed, how it assembled its massive atmosphere from the primordial gas and dust disk, and what the conditions of the early solar nebula look like. Water is the single most revealing chemical tracer for reconstructing Jupiter's origin story. Get the water abundance right, and the models of how the entire solar system formed can be sharpened immensely. Get it wrong, and the models float without an anchor. The first attempt to measure Jupiter's water came from the Galileo atmospheric probe in 1995. The probe descended into the atmosphere and took direct measurements of composition as it fell. The results were baffling. The water abundance it recorded was far lower than any model predicted, so low that it seemed to contradict basic assumptions about how a gas giant should be built. For years, scientists debated what had gone wrong. Eventually, the consensus settled on the explanation that the probe had entered an anomalous region of the atmosphere, a so-called hotspot, a dry, cloud-free downdraft where water had been driven out by local meteorological conditions. The measurement was real, but it reflected a single atypical location rather than the planet as a whole. It was as if someone had tried to measure Earth's average rainfall by dropping a sensor into the Sahara. Juno was designed to solve this problem by measuring water from orbit. Using its microwave radiometer to peer through the clouds and map water abundance, across wide swaths of the planet rather than a single point. What Juno found was that the equatorial region of Jupiter contained significantly more water than the Galileo probe had measured, suggesting the probe's entry site was indeed unrepresentative. But Juno's data also revealed that water abundance varies dramatically by latitude and depth, with puzzling regional differences that do not match any single clean formation model. The equatorial zone appears enriched, but other latitudes show different profiles, and the deep distribution remains uncertain, below the depths the microwave radiometer can penetrate. After decades of study, 2 dedicated missions, and a spacecraft that orbited Jupiter for over 9 years, scientists still cannot give a definitive answer to how much water the planet contains. That single, unresolved question, one that sounds so elementary it could appear on a grade school worksheet, has resisted every instrument and every strategy thrown at it. Jupiter does not yield its secrets easily. Its atmosphere is so deep, so variable, and so internally active that even a basic compositional measurement becomes a multi-decade scientific puzzle. The planet is not merely extreme, it is resistant to comprehension at a fundamental level, and that environment escalates faster than human intuition can follow. At the top of the atmosphere, conditions are almost familiar. Temperatures hover around negative 150 degrees Celsius. Pressure is close to what you would find at sea level on Earth. If you were floating in a specially designed balloon at this altitude, you would be in conditions that are harsh but recognizable. Cold, windy, low pressure. Dangerous, but conceptually understandable. Now descend. Within the first few 100 kilometers, the pressure climbs rapidly. The temperature rises. The hydrogen and helium gas that make up the bulk of Jupiter's atmosphere compress under the weight of everything above. The sky disappears. Light from the sun fades and then vanishes entirely. You are now inside an atmosphere so thick that it has become opaque. There is no horizon. There is no up or down in any visual sense. Only the instruments telling you that the pressure is climbing past 10 Earth atmospheres, then 50, then 100. Keep going. At roughly 1,000 kilometers below the visible cloud tops, the pressure exceeds 1,000 Earth atmospheres. The temperature has climbed past 1,000 degrees Celsius. The hydrogen is no longer behaving like a gas in any conventional sense. It is a supercritical fluid, a state of matter where the distinction between liquid and gas ceases to exist. It is too hot to condense into a liquid, but too compressed to expand freely as a gas. It exists in a strange intermediate state that does not occur naturally anywhere on the surface of Earth. If you tried to descend through this layer in any vehicle ever designed by human engineers, the pressure alone would have already crushed it. Not damaged it, crushed it completely. But Jupiter is not finished. Deeper still, around 20,000 kilometers below the cloud tops, the pressure reaches approximately 2 million Earth atmospheres. At this depth, something happens that makes Jupiter fundamentally different from any rocky planet. The hydrogen, compressed beyond anything achievable in virtually any laboratory on Earth, undergoes a phase transition. Its molecules are forced so tightly together that the electrons break free from their atomic bonds and begin to flow between atoms the way electrons move through a conducting metal. The hydrogen becomes metallic. This is not a metaphor. Metallic hydrogen is a real physical state that scientists have struggled to create on Earth, even in the most extreme high-pressure experiments using diamond anvil cells. On Earth, producing it requires pressures above roughly 4 million atmospheres and maintaining it for more than a fraction of a second is nearly impossible. Jupiter produces it naturally across a layer that extends for approximately 25,000 kilometers. A sea of liquid metallic hydrogen deeper than the diameter of two Earths, stacked end to end, existing in total darkness, under pressures that climb toward 45 million Earth atmospheres as you approach the core. This metallic hydrogen ocean is not an inert feature. It is the engine that powers one of the most dangerous aspects of Jupiter. An aspect that you cannot see and cannot feel, but that would kill you faster than the storms, faster than the pressure, faster than anything else the planet can do. Jupiter's metallic hydrogen interior conducts electricity, and because the planet rotates once every 10 hours, that electrically conducting ocean spins at enormous speed, generating a magnetic field of extraordinary power. A magnetic field that traps and accelerates charged particles into radiation belts, so intense that they constitute the deadliest environment in the planetary solar system. But that story belongs to what comes next. For now, what matters is this. The planet you thought you knew, the one on the poster, the one with the pretty stripes, is a world with no ground, no surface, no place to stand. Its atmosphere is a permanent engine of wind, storm, and pressure that begins at familiar values and escalates into conditions more extreme than the interior of most stars. Its cloud-top storms are merely the visible signature of systems that plunge thousands of kilometers into a body where hydrogen itself is tortured into states of matter that barely exist anywhere else in nature. Its core, if it exists as a distinct structure, sits at temperatures that may exceed 30,000 degrees Celsius, hotter than the surface of the sun under pressures that exceed 45 million times the atmospheric pressure at sea level on Earth. Juno's gravity measurements revealed that even the core is not what scientists expected. Instead of a dense, compact ball of heavy elements, the data points toward a dilute core, a region where heavy elements are mixed into the surrounding metallic hydrogen rather than concentrated at the center. The interior of Jupiter is not neatly layered like a textbook diagram. It is blurred, violent, and structurally more complex than any pre-mission model predicted. And Jupiter radiates more energy than it receives. This detail passes most people by when they encounter it, but it should stop you in place. Jupiter emits roughly 1.5 to 2 times as much energy as it absorbs from the sun. The planet is not simply reflecting sunlight and glowing passively. It is generating heat from within, driven by a slow gravitational contraction that has been ongoing since the planet formed 4.5 billion years ago. Jupiter is still shrinking, still compressing, still converting gravitational potential energy into thermal energy at a rate of roughly a few centimeters per century. It is, in the most literal sense, a world that is still forming, still releasing the energy of its own creation, still radiating heat outward from an interior so extreme that it blurs the line between planet and failed star. That comparison is not casual. Jupiter is composed primarily of hydrogen and helium, the same elements that make up the Sun. If it had been roughly 80 times more massive during its formation, the pressure and temperature at its core would have ignited hydrogen fusion, and Jupiter would have become a star. It did not reach that threshold, but it came closer to stellar ignition than any other planet in this solar system, and its internal conditions reflect that proximity. The core temperature, the metallic hydrogen ocean, the self-generated heat. These are not planetary features in the way that valleys and craters are planetary features. They are features of an object that sits on the boundary between two categories of existence, planet and star, and belongs fully to neither. This is the world you were taught to call a gas giant, a term that sounds almost gentle. Giant, yes, but gas, a word that evokes something light, something diffuse, something that spreads thin and dissipates. Jupiter is the opposite. It is dense, compressed, self-heating, storm-wrapped, and structurally extreme from its outermost cloud to whatever sits at its center. Every layer is more violent than the one above it. Every measurement that Juno returned made the planet less familiar, not more. The Juno mission transformed our understanding of Jupiter's atmosphere and interior across more than 70 orbits. Its microwave radiometer mapped ammonia distribution deep below the clouds and found it wildly uneven, concentrated in some bands and depleted in others, suggesting convective processes of enormous power pulling material up and down across vast distances. Its gravity science experiments measured tiny variations in the spacecraft's orbital trajectory caused by irregularities in Jupiter's internal mass distribution. And from those variations, scientists reconstructed a picture of an interior far more turbulent and mixed than the clean three-layer models that had dominated textbooks for decades. The deep atmosphere, the liquid hydrogen envelope, the metallic hydrogen ocean, and the core are not separate compartments. They interact. They exchange material and energy across boundaries that may not even be sharp. Jupiter is not a planet with weather on top and structure underneath. Jupiter is weather. It is structure. It is a single continuous system of escalating violence from the first wisp of ammonia cloud to the deepest reach of its core. And the storms you can see, the Great Red Spot, the polar cyclones, the swirling white ovals that chase each other around the equatorial bands, those are the least of it. Those are the part Jupiter lets you see, the part it shows to every telescope and every passing spacecraft, and every child who looks up at a bright point of light in the night sky and says the name they learned in school. What Jupiter does not show so easily is what lies beyond its atmosphere. Not deeper. Beyond. Extending outward in every direction for millions of kilometers. Invisible to the naked eye, undetectable by any human sense. A structure so vast that if you could see it from Earth, it would appear several times wider than the full moon in the sky. The largest structure in the solar system is not the sun. It is not the Oort cloud. It is the magnetic field that Jupiter generates from its spinning metallic heart. A field that reaches out into space, traps particles, accelerates them to relativistic speeds, and wraps the planet in a cocoon of radiation so intense that it has damaged every single spacecraft that has ever ventured close enough to study it. The storms were the introduction. The pressure was the warning. What comes next is the weapon. There is something surrounding Jupiter that you cannot see, cannot hear, and cannot feel from any distance that would still leave you alive. It has no color. It produces no sound that travels through the vacuum of space. It does not glow in visible light, and no photograph from any consumer telescope will ever show it to you. But it is there. It has been there for billions of years, and it is, by a wide margin, the single largest structure produced by any planet in the solar system, Jupiter's magnetosphere. If you could somehow make it visible, if you could paint it in light and hang it in the sky, it would dwarf everything else you have ever seen in space. On average, Jupiter's magnetosphere extends roughly 20 million kilometers across. That is approximately 150 times the diameter of Jupiter itself. It is nearly 15 times the diameter of the Sun. If you were standing on Earth and Jupiter's magnetosphere could be seen with the naked eye, it would span several times the apparent width of the full moon. It is so large that the solar wind, the constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second, has to flow around it the way a river flows around a boulder. On the side facing away from the Sun, Jupiter's magnetotail, the elongated shadow of its magnetic influence, stretches outward for hundreds of millions of kilometers. It can reach as far as the orbit of Saturn. The magnetic influence of a single planet touching the orbital space of another planet nearly 1.5 billion kilometers from the Sun. That fact alone should reshape how you think about Jupiter. This is not simply a big planet with big weather. This is a planet whose invisible influence extends across a volume of space, so enormous that it constitutes its own environment, a magnetic empire wrapped around the physical body of the planet like an atmosphere made not of gas, but of force. And inside that empire, the conditions are lethal. Before scientists ever sent a spacecraft to Jupiter, the planet announced its electromagnetic violence from across the solar system. In 1955, two radio astronomers named Bernard Burke and Kenneth Franklin were testing an antenna array at the Carnegie Institution in Washington when they detected powerful bursts of radio noise coming from a fixed point in the sky. The signal was not steady. It crackled and roared in intense pulses that repeated with a period of roughly 10 hours. After eliminating every terrestrial source they could think of, they traced the signal to Jupiter. The planet was screaming in radio waves. That discovery was one of the most startling moments in mid-20th century astronomy. No one had expected a planet to be a powerful radio source. Stars emit radio waves, galaxies emit radio waves, but planets were supposed to be quiet. Jupiter was not quiet. It was the loudest natural radio emitter in the solar system after the Sun itself. And the mechanism producing those emissions, high-energy electrons spiraling through an enormously powerful magnetic field and radiating energy as they accelerated, pointed to a magnetospheric environment of extraordinary intensity. The radio emissions were the first evidence that Jupiter possessed a magnetic field far stronger than Earth's. They were the first clue that the planet was surrounded by trapped charged particles energetic enough to produce synchrotron radiation, the same type of emission generated by particle accelerators on Earth. Before any probe had crossed the orbit of Mars, Jupiter was already broadcasting the signature of its own violence across interstellar distances. Every radio telescope on Earth that pointed at the right frequency could hear it. The planet was not hiding. It was announcing itself. Humanity simply had not been listening on the right channel. To understand why the magnetosphere is so powerful, you need to understand what generates it. Earth has a magnetosphere. It is produced by the motion of liquid iron in Earth's outer core, and it extends into space far enough to deflect most of the charged particles streaming from the Sun. Without it, the solar wind would gradually strip away Earth's atmosphere, and the surface would be bathed in radiation intense enough to sterilize exposed biology. Earth's magnetosphere is a shield. It is one of the reasons you are alive. Jupiter's magnetosphere is not a shield. Jupiter's magnetosphere is a weapon. The difference comes down to scale, composition, and source material. Earth's magnetic field is generated by a core of liquid iron, roughly 3,400 kilometers in radius. Jupiter's magnetic field is generated by an ocean of liquid metallic hydrogen roughly 25,000 kilometers deep, spinning once every 10 hours. The result is a magnetic field with a total dipole moment approximately 20,000 times greater than Earth's. 20,000 times. That number is not a misprint, and it is not an exaggeration. It is a direct measurement confirmed by multiple spacecraft across multiple decades of observation. A magnetic field that powerful does not simply deflect charged particles. It captures them. It traps them in looping paths along magnetic field lines. And then it accelerates them. Where the field meets the onrushing solar wind, a violent boundary forms. The solar wind, a supersonic stream of charged particles flowing outward from the sun, slams into Jupiter's magnetic field and is forced to abruptly decelerate. The result is a bow shock, a standing wave of compressed plasma that wraps around the front of the magnetosphere like the shock wave in front of a bullet. Jupiter's bow shock is the largest shock structure in the solar system, after the heliosphere's own termination shock. It fluctuates in size as the solar wind pressure changes, breathing inward when the solar wind intensifies and expanding outward when it weakens. Behind the bow shock sits the magnetopause, the outer boundary of Jupiter's magnetic domain. This boundary is not a static wall. It ripples and deforms under the constant pressure of the solar wind. And occasionally, when solar wind conditions change rapidly, the magnetopause can be pushed inward by millions of kilometers in a matter of hours before rebounding outward again. Jupiter's magnetic empire is not a rigid fortress. It is a living, breathing structure that responds to external pressure while maintaining its internal regime of trapped particles and accelerated radiation. Inside that boundary, the radiation environment is extraordinary. Jupiter's radiation belts are similar in principle to Earth's Van Allen belts, two donut-shaped regions of trapped charged particles encircling the planet. But where Earth's Van Allen belts contain particles with energies measured in the low millions of electron volts, Jupiter's radiation belts contain particles accelerated to tens of millions, and in some cases, hundreds of millions of electron volts. The intensity of the trapped radiation is not modestly higher than Earth's. It is millions of times more intense. Jupiter's radiation belts are, in terms of energetic particle flux, the most extreme environment in the solar system outside of the sun itself. The particles trapped in those belts come from two primary sources. The first is the solar wind. Protons and electrons streaming from the sun are caught by Jupiter's enormous magnetic field and funneled into the radiation belts, where they are accelerated by the planet's rapid rotation and the complex dynamics of the magnetosphere. But the solar wind alone does not account for the extraordinary intensity of Jupiter's radiation environment. The second source is far stranger and far closer to Jupiter itself. Io, Jupiter's innermost large moon, orbiting just 422,000 kilometers from the planet's center, is the most volcanically active body in the known solar system. Its surface is covered in active volcanic vents, sulfur dioxide frost, and lava flows that reshape the landscape continuously. Io's volcanism is not driven by internal radioactive decay the way Earth's volcanism largely is. It is driven by Jupiter. The gravitational tidal forces exerted on Io by Jupiter, amplified by the orbital resonance Io shares with Europa and Ganymede, flex the moon's interior so violently that rock melts. The friction generated by the constant tidal squeezing produces enough heat to keep Io in a state of perpetual, geological eruption. Juno's close flybys confirm that Io's eruptions are among the most energetically violent geological events in the solar system, with individual volcanic features releasing more power than entire civilizations produce. That output feeds directly into Jupiter's magnetosphere. Those eruptions matter for the radiation story because they eject enormous quantities of sulfur dioxide and other volcanic gases into space. Once in space, those molecules are ionized by solar ultraviolet radiation and by Jupiter's own magnetospheric environment. The ions, sulfur and oxygen atoms, stripped of their electrons, are swept up by Jupiter's rotating magnetic field and spread into a vast torus of plasma encircling Jupiter at roughly Io's orbital distance. This structure, called the Io plasma torus, is a ring of electrically charged gas that feeds directly into the radiation belts. The numbers are staggering. Io ejects roughly 1 ton of material per second into Jupiter's magnetosphere, every second. That volcanic exhaust, once ionized and captured by the magnetic field, becomes fuel for the radiation belts. The particles are accelerated by the rotation of the magnetosphere, gaining energy as they bounce back and forth along magnetic field lines between Jupiter's north and south poles. The process is, in the most literal and precise sense of the term, a natural particle accelerator. Jupiter takes volcanic gas from its own tortured moon, ionizes it, traps it, spins it, and accelerates it to energies that rival those produced by some particle accelerators built by human physicists on Earth. The result is a radiation environment of extraordinary danger, concentrated most intensely in the inner magnetosphere, exactly where Jupiter's most scientifically interesting moons happen to orbit. But Jupiter's electromagnetic relationship with its moons goes further than simply bathing them in radiation. The magnetosphere does not merely surround Io, it is wired to it. As Io plows through Jupiter's rotating magnetic field at orbital speed, it functions as a massive electrical generator. The motion of a conducting body through a magnetic field induces an electrical current. This is the same principle that drives generators on Earth. The same physics that produces electricity in every power plant and every wind turbine ever built. Io, with its ionized volcanic atmosphere and its electrically active surface, moves through Jupiter's enormously powerful magnetic field and generates a current of approximately 3 million amperes. 3 million amperes flowing along magnetic field lines from Io to Jupiter's atmosphere and back again, through a structure called the Io flux tube. That current is not a theoretical prediction. Its effects are directly visible. Where the flux tube connects to Jupiter's atmosphere near the north and south poles, the 3 million amperes of current slam into the upper atmosphere and produce a brilliant auroral footprint. This glowing spot has been imaged by the Hubble Space Telescope and by Juno's ultraviolet spectrograph. It tracks Io's position in real time, sliding along Jupiter's auroral oval as the moon orbits. When Io moves, the footprint moves. When Io's volcanic output increases and the plasma environment around the moon changes, the footprint brightens. Jupiter's atmosphere is literally responding to the motion of a moon hundreds of thousands of kilometers away, connected to it by an invisible electrical circuit of staggering power. Io is not the only moon leaving its mark. Europa and Ganymede each produce their own, smaller auroral footprints in Jupiter's atmosphere, generated by the same principle of electromagnetic induction as they travel through the magnetic field. The footprints are fainter because neither moon has the volcanic atmosphere or the intense plasma interaction, that Io does, but they are measurable and have been confirmed by multiple observations. Jupiter is electromagnetically connected to its major satellites in a way that has no parallel anywhere else in the solar system. The planet does not simply irradiate its moons from a distance. It reaches out along magnetic field lines, draws current from their orbital motion, and writes their positions into its own atmosphere in ultraviolet light. This is not a passive system. The energy flowing through the Io flux tube alone is estimated at roughly 1 trillion watts, comparable to the total electrical generating capacity of a major industrialized nation. That energy heats Jupiter's atmosphere locally, accelerates particles to extreme velocities along the flux tube, and contributes to the broader radiation environment that permeates the inner magnetosphere. The flux tubes connecting Jupiter to its moons are not merely scientific curiosities. They are active conduits of electromagnetic violence, carrying more current than any human-built power system and dissipating energy at rates that would be considered extraordinary by any terrestrial standard. The radiation environment is so extreme and so poorly understood that the most recent National Academy's Heliophysics Decadal Survey included a dedicated mission concept called COMPASS, short for Comprehensive Observations of Magnetospheric Particle Acceleration, Sources, and Sinks. Published in 2026, the concept proposes an entire multi-spacecraft mission devoted solely to studying Jupiter's radiation belts, with an unprecedented suite of instruments covering everything from thermal plasma to relativistic heavy ions, combined with dedicated X-ray imaging of the magnetospheric environment. The fact that the scientific community considers Jupiter's radiation belts important enough and mysterious enough to justify a dedicated multi-spacecraft mission should tell you something about the scale of what we are dealing with. We have been studying Jupiter's magnetosphere for over 70 years, since Burke and Franklin first heard its radio screams, and we still do not fully understand how it accelerates particles to the energies it does, or how the radiation belts maintain their extraordinary intensity over time. Let those numbers land for a moment. At the orbit of Io, an unshielded human being would receive approximately 36 sieverts of radiation per day. To put that in context, a dose of roughly 1 sievert delivered rapidly is enough to cause acute radiation sickness. A dose of 4 to 5 sieverts delivered over a short period is fatal in roughly 50% of cases without medical intervention. 36 sieverts in a single day is not a survivable exposure. It is not close to survivable. It is an exposure so far beyond the lethal threshold that the body's cellular repair mechanisms would be overwhelmed within minutes, not hours. Death would follow within days, preceded by the systematic failure of the gastrointestinal tract, the immune system, and the central nervous system. Move outward to Europa's orbit, roughly 671,000 kilometers from Jupiter, and the situation improves only in the technical sense that it takes slightly longer to die. The radiation dose at Europa is approximately 5.4 sieverts per day. That is more than double the threshold for severe radiation sickness. A human standing unshielded on Europa's surface would begin experiencing symptoms within hours and would not survive more than a few days. Europa, the moon that scientists consider one of the most promising candidates for harboring extraterrestrial life in its subsurface ocean, is bathed in radiation intense enough to kill any unprotected biology on its surface and to destroy the molecular signatures of life in its upper ice layers. That destruction is not vague, it is chemical and it is measurable. When Jupiter's high-energy particles slam into Europa's ice, they trigger a process called radiolysis, the breaking of molecular bonds by ionizing radiation. The radiation splits water molecules into reactive fragments, hydrogen radicals and oxygen radicals, that recombine into oxidizing compounds such as hydrogen peroxide and molecular oxygen. Any organic molecules embedded in the ice, the kinds of complex carbon-based compounds that would serve as evidence of biological processes in the ocean below, are torn apart by the same mechanism. The radiation does not simply kill living things on the surface, it dismantles the chemical evidence that living things ever existed. The damage is not uniform. Scientists at NASA's Jet Propulsion Laboratory have mapped the radiation dose across Europa's entire surface, and the results vary dramatically by location. Europa's trailing hemisphere, the side that faces into Jupiter's co-rotating magnetospheric plasma, receives far more bombardment than the leading hemisphere. Near the equator on the trailing side, the radiation processes the ice so aggressively that intact biosignatures would not survive within the top centimeter of the surface. Near the poles and on the leading hemisphere, where the radiation dose is lower, recognizable molecules might persist at shallower depths, perhaps within the top meter of ice. Those radiation maps were published specifically to guide future landing site selection. They are, in effect, survival charts for molecular evidence of life, showing mission planners where they must dig deeper and where the ice might still preserve whatever the ocean delivered to the surface. This means that any future lander searching for signs of life on Europa cannot simply scoop material from the surface and analyze it. The surface has been chemically shredded by Jupiter's radiation. The lander must dig beneath the processed layer, and how deep it must dig depends on where it lands relative to Jupiter's radiation geography. The entire strategy for detecting life on one of the most promising worlds in the solar system is constrained by the damage that Jupiter inflicts on that world every second of every day. Jupiter does not merely make Europa's surface lethal to humans. It is actively erasing the chemical record of whatever might be alive beneath the ice, sterilizing the most promising habitat for extraterrestrial life in the solar system from the outside in. This is not a theoretical concern. It is a primary driver of mission design for every spacecraft ever sent or planned to be sent into the Jovian system. And the engineering history of those missions reads like a catalogue of radiation damage. When Pioneer 10 became the first spacecraft to fly through Jupiter's magnetosphere in 1973, the radiation it encountered was roughly 10 times more intense than engineers had predicted. The spacecraft survived, but its instruments were hammered. Its imaging photopolarimeter received false commands from radiation-induced electrical interference, and most of the planned images of Io were lost. Pioneer 11 followed in 1974 and encountered similar punishment. The Voyager missions in 1979 were redesigned specifically to cope with the radiation levels that Pioneer had revealed, and they still experienced significant electronic interference during their Jupiter encounters. The Galileo orbiter, which spent 8 years in the Jovian system beginning in 1995, suffered the most prolonged exposure. Galileo's total radiation dose across its mission far exceeded its original design specifications. Its tape recorder malfunctioned repeatedly. Its instruments degraded. Its star scanner, used for navigation, was blinded during close approaches to the inner magnetosphere. Engineers on the ground had to develop workarounds for radiation-induced failures that had never been anticipated in the spacecraft's original design. Galileo survived as long as it did, partly through ingenuity and partly through luck. Its continued operation became, in the words of mission scientists, something approaching a minor miracle given the environment it was operating in. Juno, the spacecraft that arrived at Jupiter in 2016, was built with the lessons of every previous mission seared into its design. At its center sat a radiation vault, a box made of titanium walls roughly a centimeter thick, approximately the size of an automobile trunk. Inside that vault were Juno's most critical electronic systems. Its command and data handling computer, its power and data distribution unit, and roughly 20 other electronic assemblies. The vault was designed to reduce the radiation exposure to those components by approximately 800 times compared to what the unshielded instruments outside experienced. Even with that protection, the mission was originally planned to last only 20 months in orbit, because engineers calculated that radiation damage would eventually overwhelm even the shielded systems. Juno exceeded that timeline dramatically, operating for over 9 years across more than 70 orbits. But it did not escape unscathed. Its JunoCam imager, mounted outside the vault and exposed directly to the magnetospheric environment, suffered progressive radiation damage that degraded image quality across the extended mission. Engineers attempted to anneal the damage by cycling the camera's heater to extreme temperatures, a technique that partially restored function but could not reverse the cumulative effects of years of bombardment. Juno's orbit was itself a concession to the radiation, rather than circling Jupiter in a tight equatorial orbit that would have passed through the densest regions of the radiation belts on every revolution. Juno was placed in a highly elongated polar orbit. It swept in close to the planet over the poles, where the radiation belts are thinnest, took its measurements during a brief window of intense exposure, and then swung back out to a distance of millions of kilometers, where the radiation was manageable. Each close approach was, in engineering terms, a controlled sprint through a lethal environment. Get in, collect data, get out, survive long enough to do it again. The missions currently en route to Jupiter have internalized this reality so deeply that it shapes their entire operational architecture. NASA's Europa Clipper, launched in October 2024 and expected to arrive at Jupiter in April 2030, will not orbit Europa. It cannot orbit Europa. The radiation environment at Europa's orbital distance would destroy the spacecraft's electronics and degrade its solar panels within weeks. Instead, Europa Clipper will orbit Jupiter in a wide, looping trajectory and perform 49 rapid flybys of Europa, swooping close to the moon's surface, collecting data for a few hours at most during each pass, and then retreating to the relative safety of the outer magnetosphere to transmit its findings back to Earth. The spacecraft will dip into the radiation danger zone briefly and repeatedly, rather than residing in it continuously. Each flyby is a calculated risk. Each retreat is a recovery period. ESA's JUICE mission, launched in April 2023 and expected to arrive at the Jovian system in 2031, faces the same constraint. JUICE will eventually enter orbit around Ganymede, the outermost of the 4 large Galilean moons, where the radiation is significantly lower than at Europa or Io. But even Ganymede's environment requires substantial radiation hardening. JUICE carries what mission engineers have described as a nuclear bunker at its core. layers of shielding designed to protect its electronics from the Jovian radiation throughout a mission that will require years of operation within the magnetosphere. And JUICE will perform only 2 flybys of Europa, precisely because lingering near that moon for any extended period would exceed the spacecraft's radiation tolerance. Think carefully about what this means. 2 separate space agencies, representing some of the most advanced engineering capabilities on Earth, have each independently concluded that they cannot build a spacecraft tough enough to survive in continuous orbit around one of Jupiter's moons. Not because of temperature, not because of distance, not because of fuel limitations, because of radiation produced by the planet's magnetic field. Jupiter's invisible environment is so hostile that it dictates the architecture of missions designed by the most capable engineers alive. And the radiation does not simply sit passively in the belts. It interacts with Jupiter's atmosphere to produce the most powerful auroras in the solar system. On Earth, auroras are caused by charged particles from the solar wind, spiraling along magnetic field lines and colliding with atmospheric gases near the poles. The result is shimmering curtains of green and purple light. They are beautiful. They are harmless. Jupiter's auroras operate on the same basic principle, but at a scale that removes any resemblance to the gentle light shows visible from northern latitudes on Earth. Jupiter's auroras are permanent. They do not come and go with solar activity the way Earth's do. They are always present, always active, driven not primarily by the solar wind, but by the internal dynamics of the magnetosphere itself, and by the charged particles supplied by Io's volcanic output. The energy involved is hundreds of times greater than Earth's auroral energy. Jupiter's auroras emit not only visible light, but also intense ultraviolet radiation and X-rays. The X-ray emissions, detected by space-based observatories including the Chandra X-ray Observatory, pulse with a regularity that scientists have spent decades trying to fully explain. The leading models involve magnetic field line reconnection events, moments where the topology of the magnetic field abruptly rearranges, releasing stored energy in bursts that accelerate ions to extreme velocities and send them crashing into Jupiter's upper atmosphere. Some of these X-ray pulses repeat on cycles of roughly 27 minutes at the North Pole, while the South Pole pulses independently on a different schedule. The 2 hemispheres of Jupiter's auroral system do not even coordinate with each other. They operate as semi-independent engines of electromagnetic violence, each driving its own pattern of particle acceleration and atmospheric bombardment. The auroras are visible evidence of the energy budget operating within Jupiter's magnetosphere, and that budget is enormous. The total power dissipated in Jupiter's magnetosphere is estimated at roughly 100 trillion watts. That is many times the total electrical generating capacity of human civilization. And it is produced entirely by the interaction between a spinning magnetic field, trapped charged particles, and volcanic material ejected from a moon that Jupiter itself is tearing apart. This is the system. Jupiter generates a magnetic field of extraordinary strength from its metallic hydrogen interior. That field creates a magnetosphere larger than the Sun. The magnetosphere captures and traps charged particles from the solar wind and from Io's volcanic ejector. The planet's rapid rotation accelerates those particles to lethal energies. Its magnetic field lines reach down to its moons and draw electrical current from their orbital motion, connecting the planet to its satellites through invisible circuits carrying millions of amperes. The The radiation it produces does not merely threaten living things. It chemically dismantles the molecular evidence of life on the surface of the most promising ocean world in the solar system. The result is a radiation environment that would kill a human in hours, that has damaged every spacecraft ever sent into it, and that forces mission designers to treat close approaches the way a combat pilot treats a run through enemy fire: fast, brief, and calculated to the second. And here is the detail that connects the radiation story to everything that comes next. The magnetosphere does not simply surround Jupiter, it reaches outward across millions of kilometers and envelopes every major moon in the Jovian system. Io, Europa, Ganymede, Callisto, all of them orbit inside this magnetic empire. Every one of them is subject to its radiation, its charged particle bombardment, its electromagnetic influence. The moons do not exist independently. They exist as captive objects within a system dominated by a planet whose power extends far beyond its physical body. That word, dominated, is the key to what follows, because Jupiter does not dominate only through radiation. The magnetosphere is the invisible expression of a deeper force, one that operates not through electromagnetic fields, but through the most fundamental interaction in physics: gravity. Jupiter's gravitational reach does not stop at its moons. It does not stop at the edge of the magnetosphere. It extends outward across the entire solar system, reshaping the orbits of asteroids, redirecting comets, and influencing the architecture of planetary formation in ways that affected whether Earth could exist at all. The storms showed you what Jupiter does to itself. The radiation showed you what Jupiter does to the space immediately around it. What comes next shows you what Jupiter does to everything else. And the answer is not protection. The answer is not the comforting story you may have heard about Jupiter being Earth's guardian, sweeping the inner solar system clean of dangerous debris. That story is simpler than the truth, and the truth is far more unsettling. Everything described so far has been about what Jupiter does to itself, and what Jupiter does to the space immediately surrounding it. The storms ravage its own atmosphere. The pressure crushes its own interior. The radiation poisons its own neighborhood. If those were the full extent of Jupiter's violence, the planet would still be the most extreme world in the inner solar system by a wide margin. But they are not the full extent. They are not even close. Jupiter's violence extends outward. It reaches across hundreds of millions of kilometers. It redirects objects, reshapes orbits, deforms entire worlds, and has been doing so for 4.5 billion years. The mechanism behind this reach is not electromagnetic, and it is not atmospheric. It is gravitational. And gravity, unlike storms or radiation, has no boundary. It does not weaken to zero at any distance. It simply weakens with a square of the distance, which means that a planet with Jupiter's mass still exerts measurable gravitational influence on objects unimaginably far away. Jupiter's mass is not just large, it is structurally dominant. Jupiter contains roughly 318 times the mass of Earth. It contains 2.5 times the mass of every other planet in the solar system combined. Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, add them all together, double the total, and Jupiter still outweighs the result. In gravitational terms, the solar system has two major players: the Sun and Jupiter. Everything else is a supporting character. That gravitational dominance begins at home. Jupiter's 4 largest moons, the Galilean satellites, orbit inside Jupiter's gravitational sphere of influence and have been shaped by that influence in ways so extreme that several of them are among the most geologically and physically interesting bodies ever studied. And in each case, the interesting features trace directly back to Jupiter's gravity, treating those moons not as companions, but as objects to be squeezed, heated, cracked, and deformed. Start with Io, the innermost of the four. Io orbits Jupiter at a distance of roughly 422,000 kilometers, completing one full orbit every 42.5 hours. At that distance, Jupiter's gravitational pull is immense, but the pull alone is not what makes Io extraordinary. What makes Io extraordinary is the way that pull varies across the moon's body and the way it interacts with the gravitational influence of the other large moons. Io is locked in what scientists call a Laplace resonance with Europa and Ganymede. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This precise orbital relationship is not coincidental. It is maintained by gravitational interactions between the 3 moons, and it has a devastating consequence for Io. The resonance prevents Io's orbit from circularizing. Instead, the orbit remains slightly elliptical, which means Io's distance from Jupiter changes throughout each orbit. As that distance changes, the strength of Jupiter's gravitational pull on the near side of the moon versus the far side changes as well. The result is a tidal bulge that shifts back and forth across Io's interior with every orbit, flexing the moon's rocky body the way you might repeatedly bend a piece of metal until it heats up in your hands. The heat generated by this tidal flexing is extraordinary. It is sufficient to melt rock inside Io's interior and maintain a state of continuous volcanic eruption across the moon's surface. Io is not volcanically active the way Earth is volcanically active. Earth has localized eruptions at plate boundaries and hotspots. Io is erupting everywhere, constantly. Its surface is coated in sulfur compounds ejected from hundreds of active volcanic vents. Lava lakes persist for years. Fresh flows repave sections of the surface faster than impact craters can accumulate, which is why Io has almost no visible craters despite orbiting in a region dense with debris. The surface is young because Jupiter's gravity will not let it age. Juno's Jovian infrared auroral mapper captured the most extreme evidence of this process during the spacecraft's close flybys. Mission scientists reported a volcanic hotspot in Io's southern hemisphere, producing eruptions with total energy output 6 times greater than the combined output of every power plant on Earth. That single volcanic feature, on a moon roughly the size of Earth's own moon, was releasing more energy than the entire industrial infrastructure of human civilization. And it was being powered by nothing more than the gravitational flexing imposed on Io by the planet it orbits. Jupiter is, in the most direct physical sense, tearing Io apart from the inside. Europa tells a different version of the same story. Orbiting farther from Jupiter than Io, at roughly 671,000 kilometers, Europa experiences less intense tidal heating. But the heating is still substantial enough to maintain a global ocean of liquid water beneath the moon's ice shell. Europa's surface is covered in a crust of water ice that may be only a few kilometers to a few tens of kilometers thick. Beneath that crust, the ocean is estimated to contain roughly 2 to 3 times the volume of all of Earth's oceans combined. That ocean exists because Jupiter's gravity, transmitted through the same Laplace resonance that tortures Io, generates enough internal friction in Europa to keep the water from freezing solid. The ice shell itself shows the scars. Europa's surface is crisscrossed with lineae, long cracks and ridges that extend for hundreds of kilometers across the ice. These features are thought to result from tidal stresses, as Jupiter's gravity flexes the ice shell during each orbit. Some regions show evidence of chaos terrain, areas where the ice appears to have broken apart, shifted, and refrozen in jumbled patterns that suggest liquid water or warm ice reaching close to the surface. Europa's entire geological identity is a product of Jupiter's gravitational manipulation. Without Jupiter, the ocean would freeze, the cracks would not form, the geology would stop. Europa would be a dead, frozen rock. The scientific community considers Europa one of the most promising places in the solar system to search for extraterrestrial life. And the reason it is promising is precisely because Jupiter's gravity has kept its interior warm enough for liquid water to persist for billions of years. But that same gravity also wraps Europa in a radiation field intense enough to sterilize its surface and destroy molecular biosignatures in the upper layers of ice. Jupiter gives Europa its ocean and simultaneously makes the surface above that ocean lethal. The Moon exists in a state of gravitational dependency, alive inside because of Jupiter, dead outside because of Jupiter. Ganymede, the largest moon in the solar system, larger even than the planet Mercury, experiences a milder version of the same tidal influence. It too is believed to harbour a subsurface ocean, though deeper and less accessible than Europa's. Its surface shows a mix of ancient, heavily cratered terrain and younger grooved regions that may have been reshaped by tidal heating earlier in the Moon's history. Even Callisto, the outermost Galilean moon and the one least affected by Jupiter's tidal forces, shows evidence of a possible subsurface ocean, though the case is less certain. Callisto matters to this story for a different reason. It marks the edge of Jupiter's kill zone. Orbiting at roughly 1.9 million kilometers from the planet, Callisto sits just beyond the most intense concentration of Jupiter's radiation belts. The radiation dose at Callisto's distance is dramatically lower than at Europa or Ganymede, though still elevated by any terrestrial standard. This difference is significant enough that NASA's Human Outer Planets Exploration Study identified Callisto as the only Galilean satellite where a crewed surface base is even theoretically feasible. Not comfortable, not safe, feasible, with heavy shielding and limited duration stays. Io is lethal in minutes. Europa is lethal in hours. Ganymede's radiation exposure poses serious long-term health risks that current shielding technology cannot fully mitigate. Callisto is the first place in the Jovian system where the word survival transitions from physically impossible to merely extraordinarily difficult. That boundary tells you something important about the scale of Jupiter's violence. You have to travel nearly 2 million kilometers from the planet before the radiation environment drops enough for a human being to have any theoretical chance of surviving even a short stay. 2 million kilometers is roughly 5 times the distance between Earth and the Moon. Jupiter's lethal radius, the sphere inside which no unshielded human could live, extends across a volume of space so vast that you could place the entire Earth-Moon system inside it multiple times and still not reach the edge. Callisto does not escape Jupiter's control. It is still gravitationally bound, still captured, still showing the marks of its orbital servitude. It is simply the prisoner with the longest chain, the one moon far enough from the center of violence that survival becomes a question rather than a foregone conclusion. 4 large moons, every one of them shaped by Jupiter's gravity, every one of them bearing the marks of being pulled, heated, cracked, or deformed by the planet they orbit. The Jovian system is not a peaceful arrangement of bodies circling a central world. It is a gravitational hierarchy in which Jupiter imposes conditions on every object within its reach, dictating their internal temperatures, their geological activity, their surface features, and in the case of Io, even the rate at which their surfaces are destroyed and rebuilt. But the gravitational story does not end at the moons. It reaches far deeper into the solar system than most people realize. Between the orbits of Mars and Jupiter lies the asteroid belt, a broad region of space populated by millions of rocky and metallic objects, ranging in size from grains of dust to the dwarf planet Ceres, which is roughly 940 kilometers across. The asteroid belt is often imagined as a dense field of tumbling rocks, but in reality it is mostly empty space. The total mass of the entire belt is estimated at roughly 4% of the mass of Earth's moon. For a region of space that spans hundreds of millions of kilometers, that is remarkably little material. Jupiter is the reason. During the early solar system, the region now occupied by the asteroid belt contained far more mass. Planetesimals, the building blocks of planets, were present in sufficient quantities that a planet could have formed there. It never did. Jupiter's gravitational influence stirred the orbits of those planetesimals, increasing their relative velocities to the point where collisions became destructive rather than constructive. Instead of gently merging and growing into a planet, the objects smashed into each other and shattered. Jupiter prevented a planet from forming. It condemned that entire region of the solar system to remain a field of debris rather than a world. More than that, Jupiter carved specific gaps into the asteroid belt through a process called orbital resonance. At certain distances from the Sun, an asteroid's orbital period forms a simple ratio with Jupiter's orbital period. An asteroid that orbits the Sun exactly 3 times for every 1 orbit of Jupiter is said to be in a 3-to-1 resonance with the planet. At these resonance points, gravitational perturbations from Jupiter accumulate over time rather than averaging out. Each small tug adds to the previous one, and over millions of years the asteroid's orbit is destabilized. It is pulled into a more eccentric path, eventually crossing the orbits of other planets or being ejected from the belt entirely. The result is a set of depopulated zones within the belt called Kirkwood Gaps, named after the astronomer Daniel Kirkwood, who first identified them in 1866. These gaps are not caused by collisions or by any force other than Jupiter's persistent gravitational influence, reaching across hundreds of millions of kilometers and selectively clearing specific orbital zones of their inhabitants. But Jupiter does not only repel objects from certain orbits, it also captures them. At 2 specific points along Jupiter's own orbital path, 60 degrees ahead of the planet and 60 degrees behind it, sit regions of gravitational stability called Lagrange points. Objects that drift into these zones can become trapped, not temporarily, but for billions of years, held in place by the balanced gravitational influence of Jupiter and the Sun. These trapped populations are called the Trojan asteroids, and Jupiter possesses the largest collection of them in the solar system by an enormous margin. Over 10,000 Trojan asteroids have been confirmed in Jupiter's leading and trailing swarms, and the true population may number in the hundreds of thousands. Some of these objects are hundreds of kilometers across. They are not orbiting Jupiter in the traditional sense. They are orbiting the Sun in the same path as Jupiter, permanently shepherded into gravitational corrals that the planet maintains simply by existing at the mass it does. No other planet holds a comparable population. Jupiter's Trojan swarms are so scientifically important that NASA launched the Lucy mission in 2021, specifically to study them, because they represent pristine remnants of the early solar system, trapped and preserved by Jupiter's gravity for 4.5 billion years. The Kirkwood gaps and the Trojan swarms are two sides of the same gravitational coin. Jupiter clears objects from orbits it destabilizes, and traps objects in orbits it stabilizes. The asteroid belt and the regions along Jupiter's orbital path are not natural features of a passively evolving solar system. They are sculpted environments, shaped and maintained by a gravitational force that has been operating without interruption since the planets formed. And now we arrive at the myth that needs to be corrected. You may have heard that Jupiter protects Earth. The story goes something like this. Jupiter's enormous gravity acts as a cosmic shield, sweeping up or deflecting dangerous comets and asteroids that would otherwise threaten the inner solar system. This idea gained widespread popularity in the 1990s, partly through the work of George Wetherill, whose computer simulations suggested that a Jupiter-mass planet was essential for reducing the impact rate on terrestrial worlds. The timing coincided with the spectacular impact of Comet Shoemaker-Levy 9 into Jupiter in 1994, which seemed to provide vivid visual proof that Jupiter was catching bullets meant for the rest of us. The truth, as more recent research has revealed, is considerably more complicated and considerably less comforting. Jupiter does deflect some objects, specifically long-period comets originating from the Oort cloud, the distant reservoir of icy bodies surrounding the solar system, are sometimes gravitationally ejected by Jupiter before they can reach the inner solar system. In this narrow sense, Jupiter does reduce the flux of one category of potential impactor, but long-period comets represent only a small fraction of the total impact threat to Earth, perhaps 5% or less. For the other 95%, Jupiter does something very different. Multiple independent studies published over the past 2 decades, including simulations far more sophisticated than Wetherill's original work, have shown that Jupiter actually increases the rate of impacts from short-period comets and near-Earth asteroids. The mechanism is the same gravitational influence that carved the Kirkwood gaps. Jupiter perturbs the orbits of objects in the asteroid belt and in the population of icy bodies called centaurs, which orbit between Jupiter and Neptune. Those perturbations can redirect objects onto trajectories that cross the inner solar system. Jupiter does not simply absorb incoming threats, it manufactures new ones. A study published in 2024 reinforced this finding, reporting that simulations of solar systems without a Jupiter-mass planet actually showed lower impact rates on Earth-like worlds from asteroids and short-period comets than our own system experiences. The research suggested that rather than being a shield, Jupiter effectively targets the inner solar system by converting objects that would otherwise have remained in distant, safe orbits into potential impactors on Earth-crossing paths. Jupiter is both shield and sniper. It blocks some threats and creates others. And the net effect, when all categories of impactors are accounted for, is not the clean narrative of protection that the popular story suggests. The Planetary Society, in a 2024 summary of the current scientific understanding, stated plainly that Jupiter's reputation as protector of the inner solar system is not clear-cut. The Shoemaker-Levy 9 impact itself illustrates the duality with a vividness that no simulation can match. The story begins not with the impact, but years earlier, when Jupiter's gravity reached out and captured a passing comet, pulling it into a temporary orbit around the planet. The comet, designated D Shoemaker-Levy 9, had likely been wandering the outer solar system for millions of years before Jupiter snared it. Once captured, the comet's orbit brought it dangerously close to Jupiter on each pass. In July of 1992, it crossed inside the Roche limit, the distance at which Jupiter's tidal forces exceed the comet's own internal cohesion. The comet did not survive the encounter intact. Jupiter's gravity tore it apart, shredding a single body into a chain of at least 21 fragments that spread out along the orbital path like pearls on a string. For 2 years, the fragment train orbited Jupiter in silence. Astronomers watched. They calculated. They knew what was coming. And in July of 1994, over the course of 6 days, the fragments slammed into Jupiter's atmosphere one by one in the first collision between 2 solar system bodies ever observed in real time by human instruments. The impacts were staggering. Each fragment struck Jupiter's atmosphere at roughly 60 kilometers per second. The largest fragments produced fireballs that rose thousands of kilometers above the cloud tops, momentarily outshining Jupiter itself at certain wavelengths. The impact scars, dark bruises of heated gas and pulverized cometary material were visible through backyard telescopes on Earth. Some of those scars were larger in diameter than the entire Earth. The energy released by the largest individual impacts was estimated at several hundred times the combined yield of every nuclear weapon ever built by human civilization. And these were fragments, not the original intact comet. The full body, before Jupiter tore it apart, would have delivered an impact orders of magnitude more powerful. That event is often cited as evidence that Jupiter catches dangerous objects. And it did catch that one. But the reason Jupiter caught it is that Jupiter's gravity captured the comet in the first place, pulling it into a Jovian orbit years before the final impact. Jupiter created the scenario and then resolved it, like a fire department that both sets and extinguishes its own fires. The violence was entirely of Jupiter's own making. The gravitational influence extends further still. Current models of solar system formation suggest that Jupiter did not simply form quietly in its current orbit and remain there. The Grand Tack hypothesis, one of the leading models for early solar system evolution, proposes that Jupiter migrated inward toward the Sun during the first few million years of the solar system's history, traveling as close as roughly 1.5 astronomical units from the Sun, near the present orbit of Mars. At that point, gravitational interactions with Saturn reversed Jupiter's migration, and the planet moved back outward to approximately its current position. The consequences of this migration, if it occurred, were catastrophic for the inner solar system. As Jupiter moved inward, its gravity scattered planetesimals in every direction. It depleted the region of space where Mars now orbits of the building material that Mars needed to grow into a larger planet. This may be the reason Mars is as small as it is. Earth has roughly 10 times the mass of Mars. Models suggest that without Jupiter's inward migration, Mars could have accumulated significantly more material and grown to a size comparable to Earth or Venus. Jupiter may have stunted the growth of an entire planet, but the Grand Tack did more than starve Mars. As Jupiter plowed inward through the protoplanetary disk and then reversed course outward, It scattered water-rich planetesimals from beyond the snowline, the distance from the sun beyond which water ice could remain frozen, into the inner solar system. Some of those scattered bodies are believed to have collided with the young Earth, delivering a significant fraction of the water that now fills Earth's oceans. The implications of this are profound and deeply uncomfortable. The water you drink, the oceans that regulate Earth's climate, the liquid medium in which life first arose, may exist on this planet in part because Jupiter's gravitational violence scattered the right material into the right orbits at the right time. Jupiter did not intend to deliver water to Earth. It was not acting as a benefactor. It was a massive body migrating through a disk of gas and dust, scattering everything in its path. Some of what it scattered happened to end up on a small rocky world where conditions were right for liquid water to persist. The same migration that stunted Mars and shattered the asteroid belt may have seeded Earth with the ingredient most essential for life. Jupiter's gravitational violence was simultaneously destructive and, purely by accident, creative. The Grand Tack also helps explain the structure of the asteroid belt and the distribution of different types of asteroids within it. As Jupiter moved inward and then outward, it mixed material from the inner and outer solar system, scattering water-rich bodies from beyond the snowline into the inner belt, and pushing dry, rocky bodies from the inner system outward. The asteroid belt's current compositional diversity may be a direct fingerprint of Jupiter's early migration. Jupiter's gravitational influence also extends to the cometary populations at the outer edges of the solar system. The planet's gravity plays a role in determining which Kuiper belt objects are perturbed into the inner solar system as short-period comets. It influences the orbital evolution of centaurs, the transitional objects that orbit between the giant planets and serve as a source population for Jupiter family comets. These are comets with orbital periods of less than 20 years and orbits that bring them into the inner solar system, where they can potentially cross Earth's path. Jupiter's gravity is the primary mechanism that converts distant, harmless icy bodies into inner system projectiles. Every Jupiter family comet in the solar system exists in its current orbit because Jupiter put it there. The gravitational reach extends even to the hypothetical Oort cloud itself, the vast shell of icy bodies believed to surround the solar system at distances of tens of thousands of astronomical units. While the Oort cloud is primarily shaped by galactic tidal forces and passing stars, Jupiter and the other giant planets play a role in determining which objects are ejected from the planetary region into the cloud and which are pulled back inward. The boundaries of the solar system's cometary reservoir bear the imprint of Jupiter's influence. Step back and consider the full scope of what this means. A single planet, orbiting roughly 778 million kilometers from the Sun, exerts gravitational control that extends from the innermost moons of his own system outward to the asteroid belt, inward to the orbit of Mars, and potentially outward to the Oort cloud. It prevented a planet from forming. It may have stunted the growth of another planet. It carved gaps in the asteroid belt. It trapped swarms of asteroids in its own orbital path. It redirects comets into the inner solar system. It tears one of its own moons apart from the inside. It maintains subsurface oceans on two others through the same tidal mechanism. It may have delivered the water that made Earth habitable, and it does all of this passively, without intention, without effort, simply by existing at the mass it has in the orbit it occupies. Jupiter is not merely a violent planet. Jupiter is a gravitational organizing principle for the solar system. Its influence is woven into the orbital architecture of every region of the planetary system. Remove Jupiter from the solar system in a thought experiment, and the structure of what remains changes fundamentally. The asteroid belt fills with material and possibly forms a planet. Mars grows larger. The flux of cometary impactors on Earth changes in ways that are difficult to calculate but certainly significant. The Galilean moons lose their tidal heating, their oceans freeze, and their volcanic activity stops. The magnetosphere vanishes, the radiation belts disappear, the Trojan swarms disperse, and the water on Earth's surface may never have arrived. But the solar system you would be left with is not the one that produced the conditions under which life arose on Earth. Jupiter's influence, for better and for worse, is part of the reason this solar system looks the way it does. Its gravity shaped the distribution of water in the inner system, determined which planets could grow and which could not, and set the impact rate that has driven mass extinctions and evolutionary turnover for billions of years. This is the third layer of Jupiter's violence. The first was atmospheric, the storms and pressure that make the planet itself unsurvivable. The second was electromagnetic, the radiation that makes the space around Jupiter lethal. The third is gravitational, the force that reaches across the solar system and dictates the behavior of objects hundreds of millions of kilometers away. Each layer operates on a different scale. Each uses a different mechanism. And each one, considered on its own, would be sufficient to make Jupiter the most physically dominant planet near Earth. But Jupiter does not operate one layer at a time. It runs all three simultaneously, continuously, and has been doing so since the solar system formed. What remains of this story brings all three layers together and asks the question that the title of this episode has been building toward from the beginning. What does it mean to call Jupiter the most violent planet near Earth? Not the most distant, not the most exotic, not the most mysterious, the most violent. And why does the answer to that question land differently when you realize that the planet responsible for all of this violence is one you have known by name your entire life? One you could walk outside tonight and see with your own eyes, shining calmly in the dark like any other point of light in the sky. There are 4 giant planets in the solar system: Jupiter, Saturn, Uranus, and Neptune. Each of them is massive compared to Earth. Each of them has an atmosphere composed primarily of hydrogen and helium. Each of them generates a magnetic field and possesses moons, and not one of them comes close to matching what Jupiter does. This is the comparison that gives the word violent its full weight, because Jupiter is not simply an extreme planet in isolation. It is extreme relative to every other giant world that shares this solar system. And understanding why requires looking at each of them and seeing what they lack. Saturn is the planet most often compared to Jupiter. It is the second largest world in the solar system, roughly 9.5 times Earth's diameter, adorned with the most visually spectacular ring system known. Saturn has storms. It has a hexagonal polar vortex that has fascinated scientists for decades. It has a magnetosphere. It has more than 140 confirmed moons. In many ways, Saturn looks like a smaller, calmer sibling to Jupiter. But the differences are not cosmetic. They are structural. Saturn's magnetic field is roughly 600 times weaker than Jupiter's. Its radiation belts, while present, are dramatically less intense. The Cassini spacecraft orbited Saturn for 13 years and experienced radiation levels that were manageable with standard spacecraft shielding. No titanium vault was needed. No mission was designed around minimizing time in the radiation environment. The energetic particle environment around Saturn is harsh by Earth standards, but tame by Jovian standards. It operates in a fundamentally different regime of intensity. Saturn's gravitational influence is also substantial. It shapes the Kuiper belt, influences cometary orbits, and may have played a critical role in the Grand Tack migration that redirected Jupiter's early inward journey. But Saturn's mass is roughly 1/3 of Jupiter's. Its tidal forces on its moons, while significant, do not produce anything comparable to the volcanic annihilation Jupiter imposes on Io. Saturn's moon, Enceladus, has cryovolcanic activity driven by tidal heating, but the scale is modest compared to the global volcanic resurfacing Jupiter forces on its innermost large moon. Saturn is a powerful planet. It is not a dominating one. It does not restructure the solar system around itself the way Jupiter does. Uranus and Neptune are further removed from the comparison. Both are classified as ice giants rather than gas giants, smaller and compositionally distinct from Jupiter and Saturn. Uranus has an axial tilt so extreme that it essentially rolls around the Sun on its side, producing bizarre seasonal patterns, but its magnetosphere is weak and its gravitational influence on the broader solar system is modest. Neptune has the fastest sustained winds ever measured on any planet, exceeding 2,000 kilometers per hour in some observations, which is a remarkable atmospheric statistic. But Neptune's magnetic field is roughly 700 times weaker than Jupiter's. Its radiation environment is negligible by comparison. Its gravitational influence on the inner solar system is minimal. It is a violent world in its own atmospheric domain, but its violence is local and self-contained. It does not project outward. This is what makes Jupiter categorically different. It is not simply the biggest giant planet. It is the only planet in the solar system that combines every form of planetary violence at maximum intensity simultaneously. Atmospheric violence, storms that have persisted for centuries, winds that exceed anything on any other planet in the inner solar system, pressure that crushes hydrogen into metal, internal violence, a self-heating interior that radiates more energy than it receives, core temperatures hotter than the surface of the Sun, a metallic hydrogen ocean generating the most powerful planetary magnetic field ever measured, electromagnetic violence, radiation belts millions of times more intense than Earth's, a magnetosphere wider than the Sun, energetic particle fluxes that destroy spacecraft and would kill a human in hours, gravitational violence, tidal forces that melt the interior of one moon, maintain oceans on two others, prevent a planet from forming in the asteroid belt, redirect comets toward Earth, and may have stunted the growth of Mars. No other planet does all of this. No other planet does even half of this at Jupiter's scale. Saturn comes closest, and it is not close. Now imagine descending into it. You begin at the top of Jupiter's atmosphere, hovering in a hypothetical vehicle above the cloud deck. Beneath you, the ammonia ice clouds stretch in every direction to a horizon so distant that it curves only faintly. The scale is already disorienting. Jupiter's cloudscape is not broken by continents or oceans, or any feature that would give your eye a sense of familiar proportion. It is just cloud, band after band of it, moving at different speeds, shearing against each other at the boundaries, generating eddies and vortices that are each individually larger than terrestrial hurricanes. Above you, the sky is dark. Jupiter is more than 5 times farther from the Sun than Earth is, and the sunlight that reaches this altitude is roughly 27 times weaker than what you would experience on Earth's surface. The Sun is a bright point of light, brilliant but small, offering illumination but very little warmth. The temperature at this altitude is approximately negative 150 degrees Celsius. The pressure is close to 1 Earth atmosphere. In terms of numbers alone, these conditions are survivable. Cold, dim, but survivable. You descend. Within the first 100 kilometers, the clouds thicken. The ammonia ice gives way to layers of ammonium hydrosulfide, and then to water ice and water vapor clouds. The temperature rises, the pressure climbs, light fades. The sun disappears behind an increasingly opaque atmosphere, and within a few hundred kilometers, the world around you is dark. Not twilight dark, absolute dark. There is no source of visible light. Your instruments tell you the pressure has passed 10 Earth atmospheres, then 50, then 100. You keep going. At roughly 1,000 kilometers below the visible cloud tops, the pressure has exceeded 1,000 Earth atmospheres. The temperature has risen above 1,000 degrees Celsius. The atmosphere around you is no longer a gas in any meaningful sense. It has become a supercritical fluid, a state where the difference between liquid and gas has collapsed. The medium you are moving through is dense, hot, and pressing inward from every direction, with a force that no crewed vehicle ever designed could withstand. If your vehicle were built from the strongest materials available to modern engineering, it would have been crushed long before reaching this depth. You are in a region of the planet that no human instrument has ever directly sampled. The Galileo atmospheric probe, the only object ever sent into Jupiter's atmosphere, survived for roughly 58 minutes after entry and reached a depth of about 150 kilometers before the pressure and temperature destroyed it. It transmitted data down to a pressure of approximately 22 Earth atmospheres. You are now at 50 times that depth. You keep descending. At approximately 5,000 kilometers below the clouds, the pressure has climbed past 100,000 Earth atmospheres. The hydrogen surrounding your hypothetical vehicle is now behaving as a liquid. There is no boundary, no surface you crossed, no splash. The transition from supercritical fluid to liquid is continuous. The medium just became denser, hotter, and heavier. The temperature is now several thousand degrees Celsius. You are deep inside Jupiter, surrounded by liquid hydrogen in total darkness, and the pressure is still climbing. At roughly 20,000 kilometers below the cloud tops, the environment undergoes the transformation described earlier. The pressure exceeds 2 million Earth atmospheres. The hydrogen, crushed beyond any state achievable on the surface of Earth, becomes metallic. Electrons are stripped free from their atoms and begin to flow as a conducting liquid. You are now immersed in an ocean of liquid metallic hydrogen, a substance that does not exist naturally anywhere on or near the surface of any terrestrial world. It is hot beyond comprehension, dense beyond experience, and electrically active. This is the layer that generates Jupiter's magnetic field. This is the engine that powers the magnetosphere, that fuels the radiation belts, that drives the auroras. You are inside the mechanism. The metallic hydrogen layer extends downward for roughly another 25,000 kilometers. The pressure continues to rise. By the time you approach the transition to whatever lies at Jupiter's center, the pressure has exceeded 45 million Earth atmospheres. The temperature may exceed 30,000 degrees Celsius. These conditions exceed the pressures at the center of many small stars. Whether what lies at the very center is a solid core, a diffuse mixture of heavy elements dissolved in metallic hydrogen, or something else entirely remains uncertain. Juno's gravity measurements suggest the core is not a clean, compact structure, but rather a dilute region where heavy elements are stirred into the surrounding material. Even the center of the planet resists simple description, and the entire time you are descending, for every kilometer of that journey from the cloud tops to the core, the radiation overhead never stopped. The magnetosphere continued to trap particles, accelerate them, and bombard everything within its reach. The auroras continued to pulse with more energy than human civilization generates. The moons continued to be tidally squeezed, volcanically erupted, and irradiated. The comets in the outer solar system continued to be gravitationally perturbed. The asteroid belt continued to be sculpted. Jupiter does not pause. Jupiter does not cycle between active and quiet phases, the way some geological or atmospheric systems do. Every form of violence this planet produces operates simultaneously, permanently, and at a scale that exceeds every other planet in this solar system. The storms run while the radiation screams, while the pressure crushes, while the gravity reshapes everything within reach. It is not a planet with a dangerous feature. It is a planet where every feature is dangerous. And this is the planet you can see with your naked eye on a clear night. That fact is the emotional center of this entire story. Jupiter is not a distant abstraction. It is not a concept reserved for astronomers with expensive telescopes. It is the fourth brightest object in the night sky after the Sun, the Moon, and Venus. It has been visible to every human being who has ever looked up. Ancient civilizations named it after their most powerful gods. The Romans called it Jupiter, king of the gods. The Greeks called it Zeus. The Babylonians associated it with Marduk. The Norse connected it to Thor. In every culture that named it, the planet was associated with power, authority, and supreme force. They were more right than they knew. The planet that school children learn as the big one, the one with the stripes, the gas giant with the great red spot, is in physical reality a world that crushes hydrogen into metal, generates radiation fields that would kill you faster than a nuclear reactor meltdown, sustains storms wider than planets, and gravitationally dominates the orbital behavior of objects across the entire solar system. It is the most violent planetary body in our neighborhood, by every measurable metric. And it sits in the sky looking calm, looking bright, looking like nothing more than an unusually steady point of light. The dissonance between what Jupiter looks like and what Jupiter actually is represents something important about how human beings relate to the universe. We process the cosmos through images, through names, through associations built in childhood. Jupiter to most people is a name on a chart, a photograph in a textbook, a large but unthreatening fact about the solar system. There is a distance built into that familiarity. The word Jupiter does not trigger the same instinct that the word radiation does, or the word crushing pressure, or the word lethal. It sounds like a place, a large place, maybe an impressive place, but ultimately a place that exists at a comfortable remove from daily human experience. This story has tried to collapse that distance, to take the comfortable image and show what life's behind it. Not to frighten you, but to replace a half-truth with a whole one. Jupiter is not merely large, it is not merely impressive, it is the single most overpowering and least survivable planet within the region of space that human beings have any emotional connection to. Venus is hostile, Mars is harsh, Mercury is extreme, but none of them project their violence outward the way Jupiter does. None of them dominate the behavior of objects millions of kilometers away. None of them generate killing fields of radiation that envelop their own moons. None of them sustain internal pressures that dwarf anything found in the crust or mantle of any rocky world. Jupiter does all of this simultaneously, perpetually, and on a scale that renders human engineering effectively meaningless. That last point deserves emphasis. Human beings have sent 5 spacecraft into close proximity with Jupiter. Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and Galileo all survived their encounters, though each was damaged. Juno survived 9 years in orbit, a remarkable engineering achievement enabled by a carefully designed orbit and a titanium radiation vault. Europa Clipper and JUICE are en route, carrying the most advanced radiation hardening and mission architecture ever devised for a planetary science mission. These are triumphs of engineering. They represent the best that human ingenuity can produce, and every single one of them was designed around the assumption that Jupiter's environment will try to destroy them. Every design decision, every orbit selection, every material choice, every operational timeline is built around the central reality that the planet they are visiting is an active threat to their survival. Juno did not orbit Jupiter in a circular equatorial path, because doing so would have destroyed the spacecraft within weeks. Europa Clipper will not orbit Europa, because doing so would be a death sentence for the mission. JUICE will study Europa only in 2 brief flybys, because spending more time near that moon would exceed the spacecraft's radiation tolerance. Human beings have never built anything that could survive inside Jupiter's atmosphere for more than roughly 1 hour. We have never built anything that could operate indefinitely in Jupiter's inner radiation belts. We have never built anything that could descend more than a few hundred kilometers into Jupiter's atmosphere and return. The planet is, in every practical sense, impenetrable to human technology. We can observe it. We can orbit it at a respectful distance. We can send brief, carefully designed sorties into its domain. But we cannot inhabit it, we cannot land on it, we cannot even sustain a robotic presence in its most scientifically interesting regions without accepting a ticking clock of radiation-induced degradation. And yet this planet shaped the solar system you live in. Its gravity determined where the asteroid belt would be. Its migration may have determined the size of Mars. Its tidal forces maintain the subsurface ocean on Europa, that scientists consider one of the most promising environments for extraterrestrial life. Its magnetic field generates the largest structure in the solar system. Its storms have been running since before the invention of the telescope. Jupiter is not a place you visit. Jupiter is a force you contend with. It was a force when the solar system was forming, and it will be a force long after every spacecraft humanity has ever built has been reduced to dust by its radiation and pressure and gravity. The most violent planet near Earth is not a distant object at the edge of the solar system that you have never heard of. It is the one you learned about in 3rd grade. The one you can identify in the sky without a telescope. The one whose name is so familiar that it has lost all of its menace. The title of this episode is not a metaphor. It is not an exaggeration designed to generate curiosity and then soften into something more moderate. Jupiter is, by atmospheric intensity, by internal pressure, by radiation environment, by magnetic field strength, by gravitational dominance, and by systemic influence on the wider solar system. The most violent planet near the world you live on. Every measurement supports this. Every mission has confirmed it. Every model of solar system dynamics places Jupiter at the center of the gravitational power structure that governs how objects move, where planets form, and what threatens or protects life on Earth. And the most unsettling truth is not any single number or any single measurement. It is the realization that one of the most familiar objects in the sky, one of the first planets any child learns to name, one of the brightest and most recognizable points of light visible on any clear night, is also the most thoroughly unsurvivable, the most physically overpowering, and the most systemically dominant world in the planetary neighborhood that human beings call home. The next time you see Jupiter in the sky, and you will see it because it is one of the easiest objects to find, take a moment to remember what you are actually looking at. Not a point of light, not a name on a chart, not the big one from the classroom poster. You are looking at a world that crushes atoms into metal, that wraps itself in radiation lethal enough to kill in hours, that sustains storms older than nations, that tears its own moons apart from the inside, and that has been gravitationally restructuring the solar system around itself since before the Earth existed. It has been doing all of this for 4.5 billion years. It will continue doing all of this for billions more. And it will never look like anything other than a steady, calm, bright point of light. The most violent planet near Earth does not announce what it is. It never has. It simply exists, burning quietly in the dark, daring you to look closer. And the closer you look, the less it resembles anything you were taught to call a planet.